Recording. I hope I just turned it off now as opposed to it hasn't been on the entire class. All right, so we are going to try physics by democracy. You must have an opinion, even if it's just based purely upon gut or random chance. So we got the small one, we got the big one, tie, or neither. So who thinks the small one is going to win? Who thinks the large one is going to win? Who thinks it's going to be a tie? So 1, 2, 3, 4, 5, 6.
The theme.
So it's tie. All right. Neither. So that was a 7 of you. Neither would be if one exploded on the way down. It's an homage to a Green Arrow comic book I had growing up, where they were betting on a hockey game and someone bet that neither team would win because there was an explosion in the middle of it. They quite easily figured out who the bad guy was. All right, so because of the board itself, I'm going to use this as sort of a starter right here. I'm going to let it go, and then I'm going to flip sides just in case there's some board bias. And pretty close to a tie. If size makes a difference there, then that was not a significant. It was not a significant impact. But let's switch sides just in case. And for the most part, it was a tie. Make sure that will roll. All right, so now I have these two. They're roughly the same diameter. Which of these two will win? And again, have an opinion, even if it's based on pure gut feeling. And so we've got so we'll start out with who thinks that this one will win? Who says this one will win? Who says a tie? Everyone's going for the tie. Okay. Let's make sure that's actually going to go down. And well, that one got in front of it. So let's switch sides in case there was board bias. Both times, this one got a full length ahead. So, anyone want to speculate yet about why these were in essence a tie, but this one won between these two?
This white.
The weight?
White, because it's lit white.
Oh. So let's see if we can. I mean, these have definitely at different widths. They do have. Don't have one that's same width there. me take another shot, and I have one that's the same width as the other one's just smaller. Nope. Those probably came from the same source. Those widths are about the same, but. All right, those widths are about the same. And, all right, but your argument is width makes a difference. So I want two that are roughly the same diameter but different widths. That's what I'm looking for. All right. Those are roughly the same diameter but different widths. So you would argue that this one would get down first because its width is not as big. Is that correct?
Yeah.
Okay. Let's find out. Slightly ahead. All right, width did not seem to have a significant influence, at least on the second race that we did.
Could it be because the other one wasn't hollowed out?
That this one was not hollowed out? If that is the case, ping pong balls. Ah, that's one I was looking for earlier. Well, let's see how well these do. Ooh. Yeah, I really need a ping pong ball. All right, so if it's a matter of not hollowed out, you would say this one would win between these two? That you seem unsure.
Yeah.
Well, you seem to be right there. So what about these two? This one will win? Just because it's got the sort of emptiness right there? So definitely won the first time and was slightly ahead on the second one. Sort of a questionable call. This one should have won. So not hollowed out does seem to be key. If we go on with that, we take two balls here, I have a marble, which is solid all the way through. I have this one, which I don't know what's inside. The glass marble seemed to get down first on that one, barely. If I flip the other around. What would you speculate about the inside of this one?
Hollow.
Very hollow, slightly hollow?
Slightly.
Why slightly?
Because the marble wasn't that far in front of it.
Super balls, are they solid all the way through?
Yeah.
Alright, so that's a super ball there. It feels like it, somewhat hollow. Again, taking one more shot at finding the ping pong ball, because I'm pretty sure that first lab, somebody used a ping pong ball. I don't know where it would be. All right. Yes, I don't know if I said it before, but yes, whether it's hollowed out or not becomes rather critical. Let's talk about why. Much to your delight, I'm going to go through a derivation. Again, just like when I went through the energy and the momentum stuff, it's not so that you can regurgitate it later. I'm doing it so that you see that this stuff comes from somewhere. Let's hope that's good enough. Let's take a look at kinetic energy. And you know what I'm about to ask. Get ready. What's the formula for kinetic energy?
MP square.
Slightly more enthusiasm that time than usual, so thank you. We'll work on synchronization next. But we're talking about things that are rotating. So if I have a door right here that is rotating, what do we choose? What do you know about the speed here versus the speed here?
Higher.
Why?
Because of,
You probably can connect it, that not, there's a simpler way. What is the formula for speed anyway?
The velocity.
Oop.
The velocity in the lowest point is more the velocity in the upper point.
So you said this has,
The velocity in the lowest point is more than the velocity in the upper, in the height point.
so you're saying this one, I'm sorry,
Velocity is,
said the velocity?
yeah,
You say the velocity of this is higher or lower than this?
higher in the lowest point.
Highest at the lowest point.
Yeah.
Oh, as it swings around.
Yeah,
Okay, I'll agree with that, but even just in this small section right here, if I spin this about some central axis, what can you tell me about the speed at this point right here versus this point right here? Not about where that, if this were falling, where it would be going the fastest, but just comparing these 2 points.
it would be slower. It would be slower around the axis.
Why?
Because it's not having to go as far, or it's going to go.
So what's the formula for speed? What's the formula for velocity?
Changing speed over changing time?
That would be scalar acceleration.
Changing position over changing time.
That would be velocity. And what about for speed? What would you need to know to figure out in a car if you didn't have a speedometer that worked?
The velocity and acceleration.
Way too complicated. You want to know how fast something's going. Have you ever passed by the signs that say speed checked by aircraft? Guess not. Follow-up question was, how does an aircraft know how fast you're going?
Is it just position over time?
Not position. Position's a vector. We're looking for a scalar here.
Acceleration over time?
Yeah, that would be jerk. Or I guess changing acceleration over time would be jerk. What's another word for change in position?
Displacement.
What is the scalar analog of displacement? Yeah, it's distance over time. Distance over time. Getting back to what Taylor was saying, as this thing spins around, the point on the outside has much farther to go than the point on the inside. But it takes the exact same amount of time to go through the same angle. I'm starting here, going all the way around. So if we think about an entire trip, this travels an entire, a much larger circle than this travels, but it takes the exact same amount of time. So the speed of this spot out here is bigger than the speed down here. So the question is, what do we choose for speed if I want to know the kinetic energy of something that is spinning? What speed do I pick, since the speed is not the same throughout?
The higher speed?
So whatever, how fast this is going, it sort of ignores the whole thing.
The average?
That's a possibility. How would you find the average?
Would you do the high speed minus, or would it be the high speed plus the lowest speed divided by 2?
All right, so that would basically give you the speed right there smack dab in the middle. Technically, you'd find the average speed squared, which is different than the average speed squared. So as a rough approximation, you could pick the middle spot. It's not a great approximation, but it's, you know, if you're doing back of the envelope calculations, it's probably good enough. What might make it a little bit simpler, instead of just picking the spot right there in the middle, suppose we think of this as two different objects. We got this object here, going from here to here, and then an object here, going from here to here. So now I'll just treat this as two objects. So now my kinetic energy is 1/2. The first part, why don't we call this 1 and 2? V1 squared plus 1/2 m2 V2 squared. So what would I choose for my speed of this piece right here? As a rough approximation. You could just repeat what Taylor said. I'm thinking about just this piece right here. What would I choose for the speed?
The middle again?
Yeah, speed of the middle works. And I can do the speed of the middle up here too. We have a slightly better approximation for what the kinetic energy is. But why 2 things? Why not 3? Let's break it up into 3 pieces. Now the mass of these pieces gets smaller and smaller, but my speed becomes a little bit more accurate. So I got speed here, speed in the middle here, and speed in the middle there. But why stop at 3? Why not 4? We get even better. Actually, the more pieces we break this rotating thing, it's called a door. The more things we break this door up into, the more accurate we're going to get. And so the kinetic energy is we're going to break this door up into a whole bunch of pieces. So we're going to add them all up. So this says I'm going to add stuff up. 1/2 times the mass of whatever piece it is we're talking about times the speed of that piece squared. And we're going to go from whatever the first piece is to whatever that last piece is. So if I break it up into 2 pieces, we get this. If I break it up into 3 pieces, then there's a plus 1/2 m3 v3 squared. This is just, I've broken it up into n pieces. Broken it up mathematically, I'm not actually taking an axe to the door. Broken up door into n pieces. So this is just 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared plus, go until you get bored of writing that, 1/2 m whatever the nth piece is, times speed of that squared. This is just shorthand notation for this. Recognize that 1/2 is in every single term. So I can just factor that out. So this, I can now write as 1/2 times the sum of all the mi/vi squared. Now, not necessarily clear about why we're doing this, but we're getting there. It will eventually connect to rolling the stuff down the board. Let's go back to angular speed. Omega. Near the end of class last week, we did the analog between the vector stuff and the scalar stuff. And then the formulas we can just transliterate. So since speed is change in distance over change in time, what would angular speed be?
Theta?
Okay, the angle divided by
Time?
time, yep. So as this thing rotates through some angle theta, there's actually a relationship between, well, V and omega. There's a relationship between the two. And it goes back to the definition of radians. I haven't done the radian bit with this group, right? I'm getting heads shaking no across the board here. All right. So I guess after the quiz on Wednesday, we will talk about radians. We will connect it. We'll eventually get back to the board.